All right, in the last video we talked about pH and how you can find pH from the hydrogen ion concentration. And now we're going to talk about how that relates to weak acids and the weak acid calculations that you'll find in a general chemistry course. So when a weak acid is placed in water, a small portion of its molecules will dissociate into hydrogen ions, H+, and conjugate base ions, B-. So the real life example would be taking a solid acid. So maybe you have some acetic acid, you have some solid crystals of acetic acid, and you put it into water. So acetic acid, or the acid you would associate with vinegar, is a weak acid, which means basically that when you put some of it into water, it doesn't completely dissociate. So, and when I say dissociate, I mean it starts out as one molecule and it will dissociate in water into the conjugate base and hydrogen ions, H plus and B minus. The majority of the acid molecules will remain in solution as undissociated aqueous particles. And the acid-base dissociation constants, Ka and Kb, are measures of the strengths of weak acids and bases. So basically, it's the measure of how much dissociation you have when you put a sample of that acid into water. And we have the equation for the Ka. So how we get Ka, we start out with the chemical equation, Ha plus H2O, and then reversible, so arrows back and forth, because it's a reversible reaction. A minus plus H3O plus. And then to get the constant Ka, we have products over reactants. So the reactant HA is in the denominator, and then the products H plus and A minus are in the numerator. And H plus is the molar concentration of hydrogen ions, A minus is the molar concentration of the conjugate base ions, and then HA is the molar concentration of the undissociated acid molecules. Now for Kb, the base dissociation constant, we have the reaction, the chemical reaction, B plus H2O, and then it's reversible, so we've got arrows going back and forth to BH plus OH minus. BH plus in brackets refers to the protonated base ion concentration, then OH minus with the brackets is the molar concentration of the hydroxide ions, and then B in brackets refers to the unprotonated base ion concentration. And all the concentrations are measured in moles per liter. Now we're going to move on to talking about how you can use this information to actually do calculations. So if you're in AP chemistry, gen chem, or even high school chemistry, this is something that you'll probably see. Maybe less so high school chemistry, but definitely AP chem and general chemistry. So let's say we have a solution, a 0.2 molar solution of acetic acid. And we know that the Ka is 1.8 times 10 to the negative fifth. And we want to calculate the pH with this information. So we already know that pH is equal to negative log of the H plus concentration, or the proton concentration. And basically the situation here is that somebody has taken solid acetic acid and they measured it out, and they put in enough solid acetic acid into a solution of water into a container filled with water, a vial filled with water, and we got the molar concentration to 0.2 molar. And we know that the Ka for acetic acid is 1.8 times 10 to the negative fifth. That's already given to us. So we can write a chemical equation involving acetic acid to find the hydrogen ion concentration. And we've written it out, HC2H3O2 plus H2O. And I've drawn the molecular formula here so you can see which proton is actually going to be removed to make this molecule become the conjugate base. So this HC2H3O2 is going to dissociate. That acidic proton is going to be abstracted by water, and the water is going to become H3O plus, or just H plus for our equation that we're going to use to calculate the pH. And the A minus, or the conjugate base, is now going to be C2H3O2 minus, because the original HA lost the proton. So we know that Ka is equal to the H plus concentration times the A minus concentration, so the conjugate base concentration, over the undissociated acid molecule concentration. And we know that every undissociated acid molecule, so HA, that dissociates, produces one H plus and one A minus. So we can say that the H plus concentration and the A minus concentration, we can say that's just X. They're the same. Okay, now we can go through the calculation. We have that 1.8 times 10 to the negative fifth equals X squared. over 0.2 molar, so that is 0.2 moles per liter, and then 3.6 times 10 to the negative 6 is equal to x squared, and then we have 1.9 times 10 to the negative third is equal to x equals the hydrogen ion concentration after we took the square root. So we have that the pH is equal to the negative log of the H plus concentration, which in this problem for that 0.2 molar solution is 2.7.